What's going on, everybody? This is Mr. Diamond, and we are now looking at our next section of colligative property notes. We have vapor pressure lowering. This one's a little bit weird, but basically when you add solute, it doesn't just change the boiling point or the freezing point of a liquid, but it also lowers the vapor pressure, and that is one of the weirdest definitions. This is a thing that's usually really hard for people to understand, and it's not a great way to explain it. But basically, it's the pressure of the vapor resulting from the evaporation of a liquid or solid above a sample of the liquid or solid in a closed container. So we'll try to explain this a bit, but we're not going to really go into a whole lot of details. But basically, if you think of my water bottle here, I pull it on, hopefully it's in frame. In my water bottle, I have water, and then I have an empty space that's above it. In this container, this water is evaporating, even though it's not a lot. It's not like it's boiling or anything like that, but it is evaporating still. So it's turning into a gas, and that gas is going to slowly build up above here at the top of this container, and then some of it's going to condense back, and it's going to turn into a liquid. In fact, that's probably what's going on up here at the top on this ring right here where you can see the water droplets, and some of that will drip back down, but it'll be kind of this nice cycle of evaporating and then condensing and evaporating and condensing. But the fact that it's evaporating is going to make gas go on top of this, and the fact that there's gas on top of this is going to mean, I just realized I'm eating the mic, sorry about that. The fact that there is going to be gas above this is going to exert pressure down on the liquid and is actually going to push down on the liquid. So the vapor pressure in here is from the water vapor evaporating and then pressing down upon the liquid water that's inside. And while I've got this, I'm gonna take a little sip. So what we use when we do vapor pressure lowering problems is we're going to be using what's called Raoult's law. Raoult's law says when you're making a solution, the vapor pressure of a solvent is lowered. Whatever the solvent is, it goes down by adding something to it. That lowering is in proportion to the amount of solute added. Or vapor pressure changes based on the mole fraction of solute in a given solvent. So notice this one actually uses mole fraction instead of just a vapor pressure lowering slash, or instead of our molality that we used the last time. Notice that it also only works under completely ideal behavior, which we're going to assume for every one of our problems. Mathematically, Raoult's law will look like this. The pressure of the solution, or the new vapor pressure of the solution, is equal to the mole fraction of the solvent times the vapor pressure that the solvent would have been if it was by itself. And we'll do an example problem of this, but I want to get to the last example while we're in here because there's no math with it, and that is osmotic pressure. It's our last type of colligative property. Osmosis, you may have learned, is the movement of a solvent through a semi-permeable membrane. It's moving from low to high solute concentrations. Basically, if you have a good example is in cells. Cells undergo osmosis where they have a very, very low or very high solute concentration on one side. For this example, we'll say that they have a lot of water inside and they're put into a very, very salty surrounding. The fact that there's more water on the inside, that there is a lower concentration on the inside, is going to result in that water trying to go to the outside of the membrane in order to try to make it more dilute and make it kind of a more safe environment. It wants to try to balance it out. And in doing so, it's going to cause the cell to shrivel up and to kind of shrink. And then if you do the opposite way, where you have a cell that's let's say it's a really, really salty cell, and it's put into a thing of pure water with no salt in it whatsoever, it's going to try to dilute the salt that's inside by going from, again, an area of low concentration to high concentration of solute. So there's no concentration outside, there's a high concentration inside. Water will flow into the cell and will eventually cause it to rupture and explode if it happens too much. So that's kind of osmosis. Osmotic pressure, then, is the external pressure that you have to apply to actually stop osmosis. And we're not really going to do anything with this. It's just kind of weird. There is a calculation about it, and there's a diagram that I'll probably draw on the board in class, but you don't need to know it. I would just know these two definitions and know that osmotic pressure is affected by amount of solute and not by the type of solute. So it is a colligative property. Okay, so look down below for the video of me working out a Raoult's law example problem. In the meantime, though, this has been Mr. Diamond. I hope you have a great rest of your day, everybody. See y'all.